Hi everyone, it's Japoo. I just recently finished my freshman year of college, and I took AP Calculus my senior year of high school. So today we're going to be talking about absolute value. If you want a copy of this worksheet, it is linked in the description below, as is the answer key as usual. So absolute value is a pretty tricky topic. I actually had a lot of difficulty with this. I don't even know if I ever fully got it in high school, but hopefully this worksheet will help a little bit kind of approach different problems involving absolute value. Talking about absolute value in general, it's very difficult to solve problems when you're thinking of absolute value as one function. So it would be best to get rid of the absolute value bars and then think of the absolute value problem as a piecewise function, or think of the absolute value itself as a piecewise function. So we can divide it into two different pieces, two different functions, a negative function and a positive function. So you've probably seen the absolute value graph before. It's that famous V graph. And we can divide it into two different functions via the negative sloping line, or the negative identity line, and the positive sloping line, or the positive identity line. So if we have to use the positive identity line in a problem, all we have to do is change the absolute value bars to parentheses and then continue on with the problem. So for example, the absolute value of 7 is just 7. You don't need to do anything to 7 because it's already 7. So that's why you just have to put parentheses around it. If we have to use the negative identity line in a problem, it's a little bit more tricky, but as long as you follow these steps, you should be fine. All you have to do is change the absolute value bars into parentheses and then put a negative in front of it. It's really important that you remember to put a negative in front of the parentheses if you're on the negative identity line, if you're using the negative portion of the absolute value. So for example, the absolute value of negative 7 would be positive 7 because we put that negative in front of negative 7. So this worksheet is going to be practicing absolute value when solving limit problems and derivative problems. Eventually, you'll also have to deal with integrals involving absolute value. And that's kind of a similar process. You follow a similar process as the one I'm about to explain here today, but that's for a later date. Right now, we're just doing limits and derivatives. So the first page of this video will be limits involving absolute value, and the second page will be derivatives involving absolute value. So let's talk about the steps for limits involving absolute value. So the first step, as I have written, just says plug in the number, and if you get a regular number, stop here. So that step is pretty self-explanatory. You just have to plug in the number that the limit is going to, and if you get an answer that's an actual number, you just stop and write that answer, and that's your answer. There are a few questions on this worksheet, including the first one, where you just have to plug in and write the answer. Very simple, very easy. So make sure to do this step because you might be able to just avoid doing the rest of this process if you can just stop at the first step. However, if you get 0 over 0 or infinity over infinity, positive or negative, you might want to maybe L'Hopital or solve the limit in that way that we learned in a previous video, the L'Hopital video. But we don't really know how to take the derivative of an absolute value, right? So our goal will be to actually get rid of the absolute value, so we might be able to L'Hopital or do some other process to solve the limit. So what I like to do is split the absolute value into two one-sided limits. So we can take the limit of the negative and positive sides of the absolute value individually. After we split up the absolute value into two one-sided limits, we can plug in the appropriate number to determine how to correctly get rid of the absolute values. So, for example, do we need to put the negative in front of the parentheses when we change the absolute value bars into parentheses or not? So after we plug in the appropriate number, and kind of determine whether or not we need to put the negative in front of those parentheses, we should have no absolute value bars. So then all we have to do is solve the limit as you would a normal limit question, whether it be L'Hopital, or maybe you want to use heaviness if you have a problem with a limit going to infinity. So following these steps should make limit problems pretty simple. If you want to write them down, you definitely can. I will probably be repeating them a lot of times during this video, so be prepared for that. And you can always rewind if you want to get a look at them again. All right. So now moving to our first problem. As I mentioned before when we were writing the steps, the first problem, we're just going to get an answer as soon as we plug in the number. So if we plug in 3 for x, we're going to get 2 times 3 plus, in the absolute value bars, 3 minus 3. So 3 minus 3 is 0. So we're going to get 6 plus 0 equals 6 for our answer. All we have to do is plug in 3 and we're done with the problem. 6 is our answer. Moving on to number 2, it's a little more tricky. We do have to do all of our steps to figure out how to solve this problem. So if we plug in 3 for x, we're actually going to get 0 over 0. And so in this problem, we actually don't have to split it into one-sided limits since we have that little minus sign next to the 3, or after the 3, excuse me. The minus sign, or the negative sign, means that the limit is coming from the left side of the graph. So we want to plug in a number like 2.9 or 2.99 to get rid of the absolute value. So as you can see, I wrote here 2.9 minus 3 is less than 0. So if it was greater than 0, we would be coming in from the positive side or the right side of the graph. But since it's less than 0, we're coming in from the left side, the negative side of the graph. All right. And so since we're coming in from the negative side of the graph, to get rid of the absolute value bars, we're going to change the absolute value bars into parentheses and then put a negative in front of the absolute, or in front of our new parentheses. So we'll get a negative in parentheses x minus 3 over 3x minus 9. Right, and if we plug in 3 into that limit, we're actually going to get 0 over 0. So our final answer will have to come after we do L'Hopital. So we just use L'Hopital on that limit, which means that we take the derivative of the top and take the derivative of the bottom. And that's going to give us negative 1 over 3 as our answer. All right, so moving on, our next problem is number 3. If you plug in the number that the limit is going to, in this case, 6, you're going to get 0 over 0. I forgot to write that step, but make sure you guys do it, because in case you get an actual number like number 1, you don't have to go through this long process. But anyway, for this case, we do get 0 over 0, so that means that we're going to split up this limit into 2 different limits. So as you can see, we split it up between a limit coming from the left side and a limit coming from the right side. Now we're going to determine which limit is coming from the left side and which limit is coming from the right side. And we do that by plugging in a number kind of close to whether or not, to like the left side of the number and then the right side of the number. So negative 6.1 minus, or yes, negative 6.1 plus 6, excuse me, I could not read my own handwriting. Negative 6.1 plus 6 is less than 0, right? And negative 5.9 plus 6 is greater than 0. So that means that the first limit is going to be coming from the left side of the graph, the negative side, and the second limit will be coming in from the right side. So when we actually write that, when we change the absolute value bars around the x plus 6 to parentheses, we get to put a negative in front of it for the first limit. Exactly. And then we are just going to change the absolute value bars into parentheses for the second limit. And if we actually plug in 6 to both of our new one-sided limits, we're going to get 0 over 0 for both of them. Since we get 0 over 0 for both of them, that means we're going to have to do L'Hopital for both of them to get the correct answer for our limits. So as you guys probably remember, we're going to take the derivative of the top and take the derivative of the bottom. And that gives us a final answer of 2 over negative 1 for our first limit, for our negative approaching limit, I think is how you say it. And then we're going to do L'Hopital again for our second limit, the positive 1. And we're actually going to get 2 as our answer for that. So since negative 2 and 2 are not equal, the limit of x going to negative 6, 2x plus 12 over the absolute value of x plus 6 does not exist. So when you're doing a problem like this, basically what you want to do is split up the absolute value into two one-sided limits and then eventually compare the answer to find whether the limit as a whole exists or not, and if it does, what the limit is. So in this case, since they are not equal, the limit does not exist. I forgot to write does not exist on the paper, but know that this limit for number 3 does not exist. Does not exist is the answer. Okay, number 4. So if we plug in 0 to the original problem, we're going to get 0 over 0. I forgot to write that again, but just know if you plug 0 into 1 over x minus 1 over the absolute value of x, you're going to get 0 over 0. Since we get 0 over 0, we are going to have to figure out whether this limit, which is already technically a one-sided limit since there's the negative after the 0 in the problem, we have to figure out whether it's coming from the negative side or the positive side. So we're going to plug in negative 0.1, and we find that that is less than 0, which means that it is coming in from the negative side. So we're going to have to put a negative in front of our x. So if you kind of look at what I've done, I've written 1 over x, that stays the same, and then we know that that used to, that addition sign in between the two 1 over x's used to be a minus sign, but then we had 1 over negative x, right? Because we added a negative since we're changing the absolute values into parentheses and then adding a negative. Technically, that negative that's now a positive sign would go outside of the parentheses, but since it's only an x, it doesn't really matter where it goes. It means the same thing. But then, since two negatives make a positive, I went ahead and indicated that we're adding 1 over x plus 1 over x. So 1 over x plus 1 over x eventually gives us 2 over x. And if we plug in 0 to the bottom of x, you're going to get negative infinity. if you plug in a very small number, or if you plug in a very small negative number, which is what you would plug into this limit, you're going to get negative infinity. A very small negative number at the bottom of this fraction, at the bottom of any fraction, in the denominator, of any fraction, will give you a negative infinity. All right. So moving on to number 5, we're going to do our first step of just plugging in 2. So that will give us 2 plus 2 over the absolute value of 2 plus 2. And we'll see that the absolute value of 2 plus 2 is just 4. So we'll get 4 over 4, and that equals 1. So again, all we had to do in this problem was plug in, and then we got the answer. We didn't have to do any splitting of the limit or anything like that. All right, so moving on to number 6, we have a limit with x going to negative infinity. So what we're going to do here is first, if we plug in negative infinity for all of our x's, we will get negative infinity over negative infinity, which means that we have to do the rest of our steps in this process. So as you can see, so negative infinity will always be less than 0 because any negative number will be less than 0. So that means that we are going to be dealing with the negative line of the absolute value. And so that means that we have to put the negative in front of the parentheses and all of that. So when we're going to rewrite our limit to get rid of the absolute values, we will replace the absolute values in the numerator with parentheses and then put a negative in front of that. So since we're doing a limit involving infinity, we can actually use our heaviness rules. And in this case, this limit would be same heavy. So the answer would be -1. And basically that's because if we look at the leading exponents and find that the ratio, if we look at the leading exponents and find that they're the same value, then we can find the ratio of the coefficients of the leading exponents to give us our answer. And that's why it's called same heavy, because the leading exponents are the same. So in this case, it's -1. And now we're going to do number 7, and as you can see, that's also a limit involving infinity. So we're going to kind of apply this, a similar process that we did in the first one. So we already know that it's going to be negative infinity over negative infinity. So we're going to check whether we're using the negative or the positive line of the absolute value. And negative infinity, again, is always going to be less than 0. So that means that we're using the negative line, which means that we have to put a negative in front of our absolute value turned parentheses. Right. So we're going to put a negative in front of 2x, which will be in parentheses. And again, we can use same heavy. We can look at the leading exponents and find the ratio of coefficients. So we will get -2 over 3 as our answer. And that's our last limit for this video. And now we're moving on to derivatives. So the first problem, number 8, asks us to prove that f of x is equal to the absolute value of x. Prove that f of x equal to the absolute value of x, that's our function, is continuous at x equals 0. Excuse me. So we're trying to prove that this function is continuous at this point. So first, let's talk about the definition of continuous. The definition of continuous is the limit of that function with x going to that point is equal to that function at that point. So what you're going towards should equal what's actually there. All right, so first we're going to deal with dividing it into a limit. So we're trying to find first the limit part, right? We're trying to find the limit of the absolute value of x. So we're going to split that limit into x, into the negative and positive side, right? So it's going to have x going to 0 with a little negative sign, and x going to 0 with a little positive sign. And as you can see, as I've written, if we plug in 0 to both of our limits after turning the absolute value into the parentheses, and for the first one adding the negative, we're going to get 0. And that means that the limit of x going to 0, absolute value of x, is equal to 0. It is equal to 0, and it does exist. So again, so basically we found the left and the right side, and if both of those sides equal each other, then the limit exists, and it exists at that point. And then we also know that f of 0 is equal to the absolute value of 0, right? So we're plugging in 0 for x, and that's equal to 0. So this limit that we just found of x going to 0 is also equal to f of 0. So f of x is continuous at x equals 0. So basically, we just proved the definition of continuous. So it's kind of good to write this sentence just to make sure that all of your work is wrapped up into one place. And that would be your answer. Number 9 is a multiple choice question. It asks, which of the following statements about f are true? And right now, f of x is equal to the absolute value of x plus 1. So what I like to do with these kinds of problems is draw a graph, because then I can kind of look at the 3 different things that I'm dealing with and see how they apply to the graph. So for my graph, I'm going to have that V shape, that classic V, that is an absolute value graph. And my point where the 2 lines meet is actually going to be at -1, right? Right. So that point, that little point, that tip is going to be at -1. Why is it going to be at -1? Well, if we look at our problem, we're trying to see where y equals 0, right? So if we make x plus 1, the absolute value of x plus 1 equal to 0, x has to be -1. So that's why that's our point. So the first thing that we're trying to figure out is if f is continuous at x equals -1, right? Well, we know that the -1 is our corner, our sharp point on this graph, but we can also see that we don't technically have to lift up the pencil at that sharp point. So when I say don't lift up the pencil, that's when you know that something is continuous. So if you're drawing that graph, you technically don't have to have like a space in between your 2 lines. It's a continuous line, right? So the first little phrase is true, right? F is continuous at x equals -1. That is true. Number 2, f is differentiable at x equals -1. Well, let's look at that. So at x equals -1, f would actually not be differentiable, because in order to be differentiable, you must be able to take the slope of the point where you're at, and you can't take the slope of -1. That does not exist. So f is differentiable at x is not differentiable at x equals -1. So that is not true. And then number 3, f has a corner at x equals -1. That is true. As you can see in our graph, there is a corner there. I wrote it down. So number 3 is correct. So then the answer choice that we would circle is D. F is continuous at x equals -1, and F has a corner at x equals -1 are both true. All right, moving on to number 10. I'm just going to check mark them. I forgot I did this. But as you can see, the first one's correct, the second one's not, the third one is. Number 10. Is the function f of x equal to the absolute value of x minus 1 differentiable at x equals 0, at x equals 1, and at x equals 2? So again, I'm going to draw a graph really fast to help me with this problem. This graph is also going to be our classic V shape for an absolute value, but the actual point, the part where it touches the y equals 0 line, will be 1. Right? So I'm going to draw a graph and I'm going to label 0, 1, and 2 because those are the 3 points that we're dealing with in this problem, right? And then I'm also going to find the slopes of my positive and negative identity lines. So the right side of the graph will have a slope of m equals 1, and the left side of the graph will have a slope of n equals -1. So taking that into consideration, we see that x equals 0, that point on f of x, is actually is on the left side of the graph, and that means that it does have a slope of -1, right? So the derivative of f of 0 would be equal to -1. That means that it's differentiable. Now, if we look at x equals 2, we'll see that that's on the m equals 1 portion of the graph, the portion of the graph where the slope is equal to 1. So the derivative of 2 in this case would be equal to 1. And again, since it has a slope, since you can take the slope of the function at that point, it is differentiable at that point. Now, our last point that we need to kind of figure out for is f of 1. And we'll find that the derivative of f of 1 does not exist since it is a sharp point. Since the derivative of f of 1 does not exist, that point is not differentiable. So x equals 0 and x equals 2 are differentiable, and x equals 1 is not differentiable. Moving on to number 11. We are again going to draw a graph to first solve this problem. So the way I drew this graph is a little bit different than normal. So I first looked at the x expression inside the absolute value, and I noticed that that's a parabola, right? So first I kind of drew the outline of a parabola in dotted lines. And then, since it's an absolute value, since there are absolute value bars around that expression, that means that there can't be anything below the y equals 0 line, right? There can't be anything below the x-axis, or can't be anything on the negative y-axis. So our actual graph is going to look a little bit different. We're just going to switch everything that would have been a negative y value up. So we're going to have a graph that looks like that, as you can see. All right, so now we have to figure out where f is differentiable in this problem. So actually, f is going to be differentiable for all x except for its sharp points. And you can kind of see where the sharp points are in the graph, and I didn't label it, but it's pretty easy to figure out. The sharp points are wherever f of x equals 0, right? So wherever the absolute value of x squared minus 9 equals 0. The absolute value of x squared minus 9 equals 0 when x is either 3 or -3, right? Because the squared gets rid of the negative. when you square a negative number, it becomes positive. So our sharp points are -3 and 3. All right, so I'm just going to write that down, and that would be our answer. All right, last question. In this question, we're going to be dealing with asymptotes. We do have a separate video on that, but I'm going to give a really quick rundown, just enough information to solve this problem. A vertical asymptote is where the denominator of f of x equals 0. So wherever the absolute value of x squared minus 9 equals 0 is where we're going to have a vertical asymptote. So to solve, what we're going to do is get rid of the absolute value bars to get x squared minus 9 equals 0, and then we're going to factor that, so we get x plus 3 and x minus 3, so x is going to be equal to a positive or -3. And the positive 3 and -3 are where we're going to have our vertical asymptotes. So that's all for part A. And now we're going to move on to part B. Part B, we're looking at horizontal asymptotes. Horizontal asymptotes are the limits of the function to positive and negative infinity. So we're actually going to find two limits in this case. So we're going to have a limit of x going to negative infinity. And then I'm just going to write down the x expression. And that's actually going to equal the limit of x going to positive infinity. And I'll show you guys why in a second. Both of those limits are going to equal 0. And that's because they're bottom heavy. Since we have a limit going to infinity, we can apply our heaviness rules. And since the leading exponent of the denominator is larger than the leading exponent of the numerator, we call this bottom heavy, and any expression that is bottom heavy is going to equal 0. So that means that our horizontal asymptote in this case will be y equals 0. And that's all the problems we have for today. So just to kind of a recap of this video, we discussed problems involving absolute value in limits and in derivatives. So if you kind of want a little recap of maybe the limit involving infinity rules, the heaviness rules, top heavy, bottom heavy, same heavy, I would definitely encourage you to check out our video on that topic. We also have a video about asymptotes. So if you're a little confused about number 12, you can definitely go check that video out. We also have a video about continuity and differentiability. So if you were confused about some of the problems earlier on this page, you could go check that video out. And while you're at it, you might as well go check out all of our other calculus videos, because I'm sure they'll be helpful and they cover a really broad range of topics that you do need to know for the AP Calculus test. If you found this video at all helpful, please give it a like and subscribe to our channel, where, as I said before, you can find a bunch of different calculus videos about completely different topics that will help you prepare for calculus and the AP test. Thanks so much.